external intercostal muscles. They pull your rib cage up and out, diaphragm down, creates a vacuum. Was expiration, exhalation, an active process normally? Was expiration, breathing out, expiration?
Passive.
Don't be looking down at shit, people. Just look at me in my face here. It's what normally what? Passive. What powers it then?
Recoil.
What powers expiration? Elastic recoil. What? Elastic recoil. Can you explain elastic recoil to me? What? Does your lung have a lot of elastic fibers around it? Yes. I'll do it all myself, Cancer. Does it have a lot of elastic fibers?
Yes.
What happens to those elastic fibers during inspiration? They're getting stretched. During inspiration, we're stretching them like stretching a rubber band. Literally no difference. So when you stop breathing in, you stop stretching them, elastic recoil is what's going to power expiration. Just the elastic recoil. But are there some times that you need to push extra air out? You need to push air out of your, primarily your expiratory reserve volume. Is there active expiration? Yes. Are there muscles involved with that?
Yes.
Yes. Those would be, we mentioned the internal intercostals and your abdominal muscles are the primary ones. The ones that you feel if you've been coughing, if you've been sick, you've been coughing for a long time, because that's active expiration, right? Coughing or laughing or crying, all right? Now, labor also, but again, that's not something you're going to be doing more than once every 9 months or so. Usually that's a maximum kind of level here. So, but for, and for our purposes, all right, coughing should be the first that comes into your mind when you think of active expiration, because when you're dealing with COVID patients, are they going to be fatigued? Are those respiratory muscles going to be fatigued? Are those patients going to be sore? Absolutely. Are they going to complain about that? Absolutely. All right, because those muscles that are used in active expiration are generally untrained muscles, because you generally don't use them that much. But if all of a sudden you have to use them 2, 3, 4, or 5 days in a row, 6 days, you're coughing for a week or so, oh my gosh, you're going to feel those muscles. So, now let's take a look at the different pressures involved, a little more detail here. First, we have to distinguish between two different terms, atmospheric pressure versus intrapulmonary pressure versus intrapleural pressure. Atmospheric pressure, as the name implies, is just the pressure out in the atmosphere. It's the pressure of the weight of gravity pulling down the several miles of water, of air molecules above us generates atmospheric pressure. 1 atmospheric pressure, roughly 760 millimeters of mercury. That's if you're at sea level. Would these pressures be higher? Don't be looking. Would these pressures be higher or lower if you were on Mount Everest? Lower. Let's try that one again. Would this number be higher or lower if you were at Mount Everest? Lower, because you're at high altitudes. There's going to be less atmosphere above you here, less pulling down. So what if you're below sea level? Higher. It's going to be higher. Intrapulmonary system is the pressure within the respiratory tract itself, within the respiratory tract. It says it rises and falls with inspiration and expiration, but eventually reaches equilibrium with atmospheric pressure. That means, let's right now, as I mentioned, we're going to set atmospheric pressure at a relative value of 0. So whatever, with this, we're setting a relative value at 0 because the absolute number, 760, all right, would be determined by whether you're at sea level, whether you're at altitude, whether you're at the dead sea, whatever it happens to be, or whether there's a storm front coming through that can change atmospheric pressure. So it's much easier just to set whatever the relative value is at 0. Does that make sense why we do this? All right. All right, now everybody take a breath and then relax. At the end of that breath, when you're relaxed, what would the pressure inside of your lungs be? What would that intrapulmonary pressure be? Well, if there's no air going in or out, the pressure in your lungs would have to be the same as atmospheric pressure. That's what they mean when they say that eventually reaches equilibrium with atmospheric pressure. Because at the end of a breath, and your glottis is open, it's going to be the same as atmospheric pressure. Would that be the same during inspiration and expiration? No. During inspiration, just think about this for a second. During inspiration, if I want to drive air in to my lungs, do I need to create an area of low pressure inside of my lungs or an area of high pressure?
Low.
I need to create an area of low pressure. Can you explain why? Why would you need to create an area of low pressure inside of your lungs in order to breathe in?
Diffusion.
Not so much diffusion as that air, like any other kind of material, has to move from areas of high to low. There has to be a gradient involved in order to move. And since we can't change the pressure on the outside, the only option is to change pressure on the inside. So, to breathe in, are you going to have to create an area of lower pressure or higher pressure? So the pressure when you breathe in has to be lower than what? Atmospheric pressure. Would that be a positive or a negative value? It would be a negative value. So when we talk about inspiration, we're talking about pressures that are intrapleural that are going to have to be what? Negative. That is, the horizontal always going to be about, oh, that's intrapleural here. That says the intrapulmonary has to rise and fall here. During inspiration, they have to be below what?
0.
Below atmospheric pressure, below 0. During expiration, then they would have to be what?
Above 0.
Above. Does that make sense? It's more important to me that this makes sense to you, that you can logically figure this out, than just memorizing these little factoids. Let's see if this pen is in there. Got something that out there. So expiration, they have to be what? Now, intrapleural pressure. Intrapleural pressure is not an air pressure. It's the pressure of the fluid inside of the pleural cavity. Intrapulmonary, what material fills your lungs? Air. Intrapulmonary pressure is an air pressure. Intrapulmonary is a what?
Air pressure.
Air pressure. Where intrapleural pressure is going to be a fluid. Because what's found inside of the pleural cavity? Serous fluid. Is there a lot? But notice it says that intrapleural pressure, the pressure within the pleural cavity, says it rises and falls with inspiration, but is always at about 4 millimeters of less than intrapulmonary, never reaching equilibrium. Why would that be? Well, remember, elastic recoil of your lungs is pulling in, right? The expansion of your rib cage is trying to pull out, all right? So those two, the rib cage pulling out, elastic recoil pulling in, creates a partial vacuum inside of those things, inside of that space. So intrapleural pressure intrapleural pressure is always going to be negative. It never gets positive. No. Okay, so intrapleural pressure again is always going to be negative. Never even gets in the positive range. So for example, give you a rough example. Let me give you a rough example of showing this one here. During inspiration, here's atmospheric pressure, 760, we'll set that at 0. During inspiration, we need to create what, a partial vacuum, correct? During inspiration. So what's happening to intrapleural pressure? Intrapleural, the air pressure is going what? Going down. Inspiration. Maybe as much as maybe -2. Expiration, what's going to happen? It's going to do what? Go up to maybe what? +2. Inspiration, it drops by 2. To get air out, it has to go up by about 2. What about the intrapleural pressures? Something's so wrong with this. Just erase the crap I just wrote on the board here. I was first talking about, no wonder you were wondering about this. Sorry, this is intrapulmonary. Why does it feel like Monday? Intrapulmonary. That's air pressure. Intrapleural. I can do this, I'm a professional. During inspiration, it's also going to be going down to maybe minus, maybe as much as maybe -8. -6 to -8. What's going to happen during expiration? It's going to be higher, it might go up to maybe -2. But notice it's still always going to be in the negative range here. Am I going to hold you accountable for these absolute values? No. But what you are going to need to know is the relative values, that intrapleural, the fluid pressure, is always going to be negative. More negative during inspiration than during expiration. Why? Because it's also going to still have to reflect what's happening in the intrapulmonary. That's why, because when during inspiration, well, intrapulmonary is going down by -2. Keep in mind that at rest, this would be at 0. This would be maybe about -4. And at rest. And at rest, we're dealing with roughly about 0 Same as atmospheric, right? For this, whereas the intrapleural, maybe closer, maybe -4. So, how does this work? Well, here's how, where we need to bring some physics into it. Who doesn't love physics, huh? And that brings us to one of our first gas laws, Boyle's law. Boyle's law, the relationship between pressure and volume. Now, this is a subset of a larger sort of general gas laws. But the key thing about Boyle's law here is if we keep temperature constant, which we're doing here, there's going to be an inverse relationship between pressure and volume. Inverse relationship between pressure and volume. Tell me about Boyle's law. Inverse relationship between what? Pressure and volume. What does this mean? During inspiration, what has to happen to pressure? It's going down, which means what's happening to the volume of your thoracic cavity? It's going up. Make sense? What's happening during expiration? During expiration, pressures are going up, which means volume has to go down. Does that make some sense? I'm hoping everybody makes some sense. I'll give you another application for this that probably has more impact, and that's on people who dive. I'm talking about like scuba divers. Anybody here got their certification for scuba? No, scuba. Okay, no scuba's here. Well, I will still share it with you. If you are, if you're just like a pearl diver, you're just holding your breath, all right? Just holding your breath, right? And roughly every 33 feet, it's roughly about that. Close enough. Don't write this number down unless you feel led to this, you're planning doing some scuba diving, but every 33 feet underwater that you are is roughly another atmospheric pressure. So if you are at sea level, how many atmospheres of pressure are you under? If you're deep diving, if you're pearl diving, you're 33 feet below water, how many atmospheres of pressure are you under? 2. Because you started with 1 at the surface, correct? And 33 feet below, you're adding 1 more. So if you're at 33 feet, you're at how many atmospheres? 2. If you're at 66 feet, you are at 3. You know how that works. So let's say right now, if you are at sea level, let's say that your total lung capacity, I'm just going to make some numbers up. If I'm a big lung person, let's say you've got 6 liters. Big lung, 6 liters. That's your total lung capacity. Let's say, but that would be your total lung capacity. You're probably not going to be, let's just say you're at 4 liters. You have 4 liters in your lungs. And now you're going to pearl dive. You're going to dive underwater 33 feet. Everybody with me? How much air is now in your respiratory system? Will there still be 4 liters if you are at 33 feet? How much air is in your lungs now? liters, and now you get to explain to me why.
You lose the liters of the rabbits.
Because there's an inverse relationship between pressure and volume. So if the pressure has doubled, then what's happening to the volume? Is the volume doubling? Or is it being cut in half? It's being cut in half. So far, so good? So this is not really a problem for you if you're pearl diving, because if you're 2 liters when you're down there at 33 feet, you're still holding your breath. You haven't let one bubble out. All right? When you rise back to the surface, that 2 liters will once again become 4 liters. But here's where it's dangerous for scuba divers. All right? Let's say you're breathing in your tank because you've got your oxygen tank, your respirator, and you're at 33 feet. You're at 33 feet. And because you're breathing through a respirator, all right, you are now have 4 liters, like you would at the surface, because you're breathing through your tank, all right? You're breathing in and out, so you got 4 liters, all right? So you're under there, you're looking around at corals, and you're looking at all the great tropical fish, and then something scares you, all right? A shark or something like this, or a squid, or a big tuna fish, whatever you happen to be afraid of, the tuna, whatever like this. And so being scared, you're gonna race to the surface. If you race to the surface with those 4 liters still in your lungs, what would that become by the time you reach the surface? It would become what? 8. What would that do to your lungs? Is that a good thing or a bad thing? Bad thing. Which is why you're taking scuba training. They will tell you, make sure that you are breathing out on your way up, so that doesn't happen to you. We hate when that happens. All right? So this has implication for scuba, but this is also explains, Boyle's law also explains why you have to have those changes in the volume of your thoracic cavity in order to affect those changes in pressure. That in order to be able to breathe in and create negative pressure, the volume has to go up, because there's an inverse relationship between pressure and volume. Better? And this is just sort of showing that during inspiration, right? The inspiratory muscles contract, the internal or the external intercostals pull your rib cage what? Up and out, all right? Diaphragm pulls down, that's going to increase the volume, so pressure is going to go down. And the reverse happens during expiration. The expiratory muscles relax, the elastic recoil pulls everything in, and air flows out. So some factors that influence this are going to be similar to factors that influence blood flow. Starting with our old friend, resistance. Most of the resistance to airflow is going to be found from the small, mid-sized bronchioles. So the ones that have the greatest ones here. During inspiration, there's going to be a little bit of a decrease in resistance. All right, as you pull the passageways open. Well, you should be familiar with these 2 different effects, bronchodilation and bronchial constriction. By the way, which of these effects, bronchodilation or bronchial constriction, would be a sympathetic effect?
Dilation.
Why dilation?
Your heart is
More oxygen.
When you're in doubt, just to go over this area. Sympathetic is fight or flight, correct? Fight or flight, correct? If you're running from the monster, do you want more air in your lungs or do you want less air?
more.
I do too. So that under sympathetic stimulation, you want your airways to dilate or constrict. Is that going to be sympathetic or parasympathetic then? That's going to be sympathetic then. And the norepi that you're going to see here is the neurotransmitter that's released by the sympathetic nervous system. Bronchial constriction then would be triggered by what? Parasympathetic. Now, there can also be irritants and inflammation that can cause that too, but parasympathetic, muscarinic receptors. Anybody muscarinic receptors now? Yeah. That was one of nine. I'm not going to torture you with that anymore. But those are airway things that would affect the diameter of your airways. Other factors that we've already mentioned, we've talked already about the alveolar surface tension that is fought by this detergent called surfactant that breaks down that surface tension, allowing you to breathe very easily here. You can we gave this example last time. Do I need to go through this again? You understand how that works and about surfactant. We talked about how babies don't develop it until late in fetal development. Just some words to know. If you hear the term pneumothorax, pneumothorax means that you've got air into that pleural cavity. Pneumo, referring to it, air, pneumothorax. And pneumothorax will often then lead to the collapse of the lung, which is atelectasis. So atelectasis is the actual act of the lung doing what? Collapsing, because of air entering, usually in that space. That was the pneumothorax. So that often you'll hear those terms seem to be used interchangeably. Oh, patient acts as pneumothorax, atelectasis. Well, it's a cause-effect kind of thing. The cause being pneumothorax, getting air into that space, that triggers the collapse, which is atelectasis, when those two membranes pull. Compliance can have an impact on breathing too. And for compliance issues, let's just cut to the chase, all right? Things like surfactant, again, without surfactant, again, the ease of opening your lungs is going to make it very difficult here. But this mobility of the thoracic cage, this is something you often get with people that are, you can often see elderly individuals with like a Dowager's hump, where they're like, humped over a lot like this. That can actually make it harder for them to breathe because they're sort of pressing on their rib cage, and it's making it difficult for the rib cage to expand. Easier here. And this last one here, elasticity of the lungs. If the lungs become fibrotic because of disease, that can reduce lung compliance. You find this in conditions like respiratory distress syndrome, where we lose that elasticity, makes it difficult to breathe. Okay. Ooh, now we get to a huge area here. Dalton's law of partial pressures. This is a biggie. Biggie. Dalton's law of partial pressure says that in a mixture of gases, like the atmosphere we're breathing, each gas contributes a percentage of the total pressure based on its percentage of the atmosphere. Which means if a gas, let's say the atmospheric pressure, I'm just going to make some numbers up. Let's say atmospheric pressure is 100. All right, you're on the top of Everest, atmospheric pressure is 100. And let's say that the air that you're breathing was 20% oxygen. What would the partial pressure of oxygen be then? If the total pressure was 100 and 20% of the air was oxygen, it would be 20. 20% of 100 is 20. So that each gas is going to contribute its partial, and here's some numbers to know. We're not going to be concerned at all about nitrogen numbers, and you'll see why in a minute here, because nitrogen is virtually insoluble unless you're at extremely high pressures. Diving Divers would need to know about nitrogen because nitrogen is insoluble at basically 1 atmosphere pressure, becomes more soluble underwater, and can cause what's called nitrogen narcosis. And they start to feel like you're tipsy, like you're a little bit alcoholic underwater like this. And if you rise too rapidly to the surface, that insoluble nitrogen starts to come out of solution, causing bubbles inside your body, causing the bends. Decompression sickness, it can kill people. But for our purposes, we're not that concerned because it doesn't get exchanged. But here's the gas that you do know. Oxygen is roughly about 21%. And since total atmospheric pressure at sea level is 760, the partial pressure of oxygen is close to 160. Just round it off to 160. That's the partial pressure of oxygen in the atmosphere. This is a good number to memorize. The oxygen in the atmosphere, 160.
I see 159.
We're rounding it to 160 because we're lazy. We're gonna do a lot of that today.